Okay, I just posted the attendance plus quick answers for you. Okay, the questions 4A, 4B, 4C are answering these. So you have to answer if any of these is 1-to-1, onto, invertible, or none of the above. So this is what you need to answer in question 4A, 4B, 4C in the attendance, and also the quiz. Okay, so just start up at Modo. You can go to the SurveyMonkey link and then put in your ID, your name, and answer these 3 questions right now. I'll give you 10 minutes. Oh, 11 minutes until 9:30. My watch. If you need some paper, I have some scrap, well, actually blank paper. Anyone need paper? Anyone else would like some paper? You can use this. You don't need to use your own. So we cover what is meant by 1-to-1 onto invertible function last class. So you can look up your notes or go online if you don't have it handy. If you remember, it's fine. One-to-one, just to remind you, means each output is mapped from distinct input. So if two input maps to the same output, then it's not one-to-one. Onto means in the codomain, in the output, all of the elements has an input. They all have inputs. So nothing in the codomain is not mapped from the domain. Invertible, actually, if you remember, means if you satisfy the first two for sure, then it would be invertible. You can check. If none of these, that means it's very easy, actually. Means that it's not one-to-one, not onto, and it's not invertible. Then you put none of these. You have 4 minutes left. You have to go to your modal, answer the survey question. And 4ABC refers to this question. Just to show you quickly, get a few minutes reminding you, invertible means function from domain to codomain is invertible if there's a function that's inverse from the B to A, codomain to the domain, such that f of x equals to y gives you f inverse of y is equals to x. So we did that algebraically. We call it inverse. And then onto means the codomain. Every element in the codomain has an output, is an output. 1 to 1 means the input, each output from in the codomain only maps to one input. And if it's both 1 to 1 and onto, then actually it is invertible. So this is what the question is asking you. So in words, that's what it means, just a reminder. And the example we gave so this is onto everything here is mapped in the output domain, but this is not 1 to 1 because two inputs map to the same output. Similarly here, it's onto, but not 1 to 1 in these two examples. So example 1 to 1 and onto is this one. Each one is mapped from an input, and each input mapped to a distinct output. So this is both onto and 1 to 1. So by definition, this is also invertible. But you have to look at the algebraic form and decide if it's 1 to 1, onto, invertible, or maybe none of these. That means it's not 1 to 1, not onto, or in that case, obviously not invertible. Let me go back to the question. I guess I'll give you 5 more minutes. Your time is already up. I'll give you 5 more minutes to answer it if you haven't done so. So there's a little twist here, if you notice. We have function f as a function of both a and b. But the concept is the same. You're mapping from natural numbers to natural numbers. Just be careful what the domain is. So these two are natural numbers. You're mapping to also domains a natural number, which is obvious. You have 2 minutes left before I close the survey. One minute left, and I'll close it. So at least answer the question. Okay, time's up. Submit it now. I'm closing it. 3, 2, 1, close. Okay, so let's start today's lecture. So the next chapter is on actually counting combinations, and also we'll touch a little bit about probability, but actually you also be giving probability in your stats course. So we won't go into too much detail. We try not to overlap. But we will go into this part because this is important. Let's consider this problem. Let's say we have 4 people, A, B, C, D, just for short, A, B, C, D. They're attending some sort of event, and they're door prizes. Door prizes means if you attend, then you get a chance to win something. So you enter the door, you come to the party, and you get a chance to win a door prize. So the question is, in how many different ways can these door prizes be awarded? So we have 2 prizes, and we have 4 people. So how do we decide who's going to get what? So this is a very general problem. You need to look at it more specifically. So let's look at the first interpretation. So if you're not given the details, you might need to make assumptions before you can answer a question. So in this case, let's assume the 2 door prizes are the same thing. Or I can say, okay, I will have a door prize for coming within 15 minutes of beginning of class. And I would give 2 prizes of a bonus mark. So how do I give it out? So in this case, the 2 door prizes are the same. That means no difference. A bonus mark is a bonus mark, for example. And we give a rule that the same person cannot win both. That means we cannot give the bonus mark to the same person, both bonus marks. One per person only. So in that case, we can list basically all the different combinations of possibilities. It could be A, B, A, C, A, D, and so on. In this case, with 4 people, you have 6 possibilities to give these 2 door prizes to. So this, if you notice, is actually in the form of a set. So set of A, B, set of A, C, and so on. So each one of these is a set. Now, like I said, if we don't specify the problem, you can have a different assumption. Let's say the 2 door prizes are different. And the same person can actually win both of them. So if for some reason I decided for the bonus mark, I can just randomly select. I can give 2 door prize. 1, a bonus mark. 2, what can I give? Maybe I have a chocolate bar. If you come on time, maybe you get a free chocolate bar next time. So I can give 2 different prizes. And the same person can actually win them both. You can have a bonus mark and have a chocolate bar. So in that case, we have more possibilities, not just 6. We actually have 12 possibilities. So we call these permutations. The thing is, the 2 door prizes are different. That means, say it's the first door prize, second door prize. So AB and BA would be different. Oh, sorry. My mistake. Same person cannot win both. So we cannot have AA, BB, CC, DD. If the same person can win both, then we can also have AA, BB, CC, DD. So this is the case, you cannot. So we have 12. The order matters in this case. So unlike before in a set, the order doesn't matter because it's the same prize. But in this case, it does because the 2 prizes are different. Okay, we call these permutations. And I'm quite sure you've heard of this before, maybe not the English word, but the equivalent in your language. And in this case, not allowed to have repeat letters because we say the same person cannot win both prizes. Again, if the same person can, if we take this out, then we can have AA, BB, CC, and DD are also possible. Like in this case. So we added AA, BB, CC, DD. So 16. Okay, again, the order matters, so this is what we call order lists. It's a list of which the order that it appears matters. Okay, so it's not really new, just reminding you of some of these terminologies. So for the last case, we go back like the first one, in the sense that 2 door prizes are the same, and then the same person can win both. So the same person can be lucky enough on a random draw to get 2 separate bonus marks. So in that case, we add AA, BB, CC, DD. So this is unordered list. We also call it sometimes a multi-set or bags. That means these things can be put in a bag, you can actually select. Okay? And the reason we don't call this a set, anybody know why we don't call it as a set? So remember the first assumption? We call these sets. But this is not a set. You can call it multi-set, but it's not a set. Can someone tell me why? Why this cannot appear in the form of a set? Can we put this as a set? Why not? There are, because same. Okay. So I think he's got the idea. In a set, given like this, if it's A, if the same person get the bonus mark, in a set, you don't put AA, you just put A. If it's a set. Because a set lists be distinct and the order doesn't matter. But if you have two door prizes or two bonus marks in this case, we cannot describe it in a set because we cannot write it in this form. That's not how you write a set properly. So we put it an order list like this. Okay? So we can look at the structure here and say, of these. Is repetition allowed? So first, second, this order matters. An order doesn't matter. So the four cases we talk about fits into here. So in the first assumption is a set. Repetition is not allowed and order doesn't matter. And the other three assumptions describe one of these. And you can look back and say which one belongs to which. Okay, does the order matter? Can the same person win twice? So it's repetition. Allow or not allow? Okay? So let's look at some more word problems. So like I told you earlier, you will encounter more and more words instead of just a question stated in mathematical form, but you'll be looking at problems like this, and you have to read, understand, and then answer the question. So you need to answer one of these. Which category does it belong to? Or which is the most appropriate you think it belongs to? First one, a state lottery game consists drawing of a ping pong ball from each of 3 machines containing 10 balls labeled from 0 to 9. Okay, so there's an additional question that asks you, how many possible outcomes are there for the game? And it says, in parentheses, a winning ticket must match the numbers drawn in the same order. So for example, you pick up 3 digits, 1, 2, 3. So the first one is a 1, second one's a 2, third one's a 3. In that order. And that matters. Anyone? So we always set the same order. That means order matters. That means here, it's one of these. Is it order list or is it permutation? Is repetition allowed? Can we have the same number appearing twice? Can it be 115? Well, if you look at this statement, it says ping pong ball. Presumably numbers 0, 1, 2, 3, 4, 6, 7, 8, 9. There are 10 of them. You draw them out one at a time. So, in a lottery that you've seen, do they allow repetition? Do they draw the number out, show it, and then put it back in, or they leave it out? They usually leave it out, right? So that means if you draw a 1, it stays outside. Only 9 of them left. So is repetition allowed or not allowed? So that means repetition is not allowed. That means it's a permutation, right? So A is a permutation. So how many possible outcomes are there for this game? How many possible outcomes? It can be 0, 1, 2, 0, 1, 3, 0, 1, 4, 0, 1, 5. So how do we calculate it? So 10 digits, and we choose 3. Nine choose 3, not 10 choose 3. Okay, so 10, you're talking about probability. So there are 10. 1 in 10 chance of getting the first one, 1 in 9 chance of getting the second one, 1 in 8 chance of getting the third one. So you're saying 10 times 9 times 8. So someone else agrees? Does that sound reasonable? The first ping pong ball is one of 10. So there are 10 possibilities. Second one only have 9 left. And then the third one has 8 left. So you can choose from 10, choose from 9, choose from 8. That means it's 10 times 9 times 8. Is that correct? Well, it's correct because it's a permutation. When I said 10 choose 3, it's for combinations. That means the order doesn't matter. But in this case, it's a permutation. Order matters. So 720 possible outcomes. 720 possible outcomes. So if you set this game and say you pay 100 baht per ticket, what price would you give out? Because it's 1 in 720 odds of winning. So you set the lottery such that, because they only, depends on how many tickets you sell, right? So you have to make that kind of, I guess, estimations. Maybe the limited number of tickets. Actually, there's no limit. Depends on how many people actually buy. And usually set it to a large price to attract more people buying. Because 1 in 720 is a pretty good chance, actually. That's only with 3. But many lottery games you've seen, it starts with 6, maybe 7, and some of them maybe even have 8, like huge astronomical number. Chance of winning is obviously almost non-existent. Okay, look at the second case. Security box guarding a sensitive area has 3 buttons colored red, green, and blue. Okay, so imagine that we have a box here, we have 3 buttons here, it's not here, but say there are 3 buttons on this box, and this is a security sensitive area. To enter the area, you must enter a security code, pressing 4 buttons in succession. So you have to choose from the 3 colors, red, green, and blue. Let's say you have to do red, green, blue, red. Very simple. Red, green, blue, red. You have to press it in that order correctly. How many different security codes are there? So before you answer that, which category does it belong to? Does the order matter? Does the order matter? It matters, right? Because if you press the wrong one first, then it's the wrong code. So the order matters. And is it repetition allow or not allow? In this case, actually allow, right? Because you can actually press the same button twice or all 4 times if you want. So we're looking at this case, an order list. So now, how many different security codes are there? You can use the same approach. The first one of 3 possibility. Second one of 3 possibility. Third one of 3 possibility. Fourth one of 3 possibility. 3 times 3 times 3 times 3. Sorry? 3 to the power 4, yes. So 81. Okay, very easy to answer, right? It's much easier than the quiz question you just answered because I explained everything here. Well, more practices. This time, let you answer it. So speaking of bonus marks, I will give bonus marks to a volunteer who come up and answer the questions correctly. So if you like bonus mark, easy mark, there's nothing to lose. The worst is you get a wrong answer, you don't get a bonus mark. So just come up and answer these on the board. And if it's correct, then you get a bonus mark. Very easy. Anybody want to do some exercise? Come up to the front. Anybody think they might need a bonus mark? I'm giving 3 bonus marks. Well, actually, this should be a D, of course, or C, sorry, or whatever. We have 2. Just forget about this label, A, E, F, doesn't make any difference. But there are 3 questions. So 3 possible bonus marks. You probably don't need it, but fine, you can go get a bonus mark if you like. Pick a question. A, E, or F, and then write down. Anyone else? We have 2 more questions left. Remember, you have to answer the question, which of the 4 finite structures would most appropriate? You have to answer that part too. So in other words, write down one of these, which one it belongs to. Order list, unordered list, permutation, or set. You need to answer that for these as well. Okay, good. Pick a question, E or F, and pick a marker. Okay, you can do it on that side. Yeah. Take your time. Anybody else? One more question? One more question left. Okay, you're done? You only answer one structure. Which finite structure you think is most closely, I guess, related to the problem? Okay, thank you. One more question. Nobody else? We need one more. Ice cream. Don't you like ice cream? Nobody like ice cream? Well, let's see if these 2 are correct. Why don't you, the rest of you, take a look to see if it's correct. Someone's allowed to... Well, I didn't bring my candy bars today, but maybe another time. So perhaps next time, if you answer a question correctly, I say, okay, you can reach in the back and pick up 2 candy bars. So it contains 5 different types of candy bars. This is the name. It's called Crazy Cat. Doesn't matter. These actually... Yeah, so there are 3 different types, sorry. Crazy Cat, Milk, Marlins Bar, and Luscious Lemon Bar. So 3 different types. In each type, there are 5 of them in there. How many different ways are there for the child to make her choice? So when you grab this, presumably grabbing as you're not seeing what's in there, so it should be random. That's the assumption you make. You did it wrong. Should we allow him to change? I already started explaining, but okay. Okay, one more. Good. Please, pick a color for E. I think that's an E. Yeah, it's a bit hard to see. Looks like they have to earn their bonus mark. Okay, so let's freeze this, meaning you cannot change anymore, okay? No more changing possible. Let's start with A. So you're allowed to grab 2 candy bars. There are 3 different types. That means you could grab the same type twice because each of these, there are 5. So it's possible to choose the 2 bars of the same type. That means repetition is allowed. And in this case, it doesn't matter the order. You can pick this first or pick that first. It doesn't matter. So this part is correct, and its unordered list is correct. That means the first time it was incorrect. Okay, but what about the answer? Does it look right to you? He's claiming chance of getting the first bar is 1 in 15. Is it? There are only 3 different types. There are only 3 different types. So we have types K, M, L. So which type is the first one you pick? One of 3 possibilities. If the probabilities are equal, like the first time it is, because each one has 5. So when you pick the first one out, it's gone. So the remaining, you still have 3 possibilities, but one of them have a lesser chance of being picked. So I can safely say, sorry, no bonus mark. You can use brute force in this case if you want, because there's only a few. K, M, L. What can it be? KK, KM, KL. It's not even that complicated. So good try. You don't need the bonus mark probably. Second part, ice cream. It's so hot out there. It's good to have ice cream, isn't it? In this case, the shop offers 8 different flavors of ice cream. You can name your 8 favorite types, doesn't matter. How many different 2-scoop dishes are possible? So in other words, you scoop one from one of the 8 flavors, and you scoop another one from another flavor. So imagine going to Swenson, and you wanted to have what? Chocolate with lime, if you want. So first scoop is chocolate, second scoop is lime. And in this case, it's not because you're going to put it in a dish, side by side. So in Swenson, instead of a cone, you choose a bowl. So they put 2 scoops in there. You have lime and you have chocolate. So in other words, the order doesn't matter. And you can choose 2 chocolate if you like chocolate. Right? So order doesn't matter, and repetition is allowed. So it looks like another unordered list. But you say permutation. So is she correct, or is there an assumption that's being made? You say repetition is not allowed and order matters. But if you read this statement, How many, see, fun words. How many different 2-scoop dishes? How do you interpret that? Meaning the 2 scoops are different? In that case, then we said repetition is not allowed. But the only question is, does the order matter? Your interpretation. The 2 scoops are placed side by side in the dish or in a bowl in the case of Swenson. You put a bowl, you put 2 scoops in there. So if you look at that scenario, the order doesn't matter. But if you answer this way, write also in word, why do you think it is the order matters? Make an assumption if you think it's not clear. If you think this is not clear, and you think the 2 scoop, the order, maybe you have to put one on the right side, one on the left side. So be more specific to answer it. So you can say it's question mark, but for my interpretation, it's probably order doesn't matter. But like I said, if you write it down, what your interpretation is, then you may be able to get full mark for this. So, repetition is not allowed, and order doesn't matter. So we actually have a set, if you go by my interpretation. Okay, so how many different 2 scoops? Let's go by her interpretation, she was correct. Let's say the order matters. Let's say the order matters. So right side and left side makes a difference. Okay? So you put it in front of you, right or left, or front and back, doesn't matter, I mean, when you look at it. Let's say it matters. Let's say this is okay. Let's say it's okay, according to your interpretation. Is this correct? See, her argument is different. She said 8 times 8, 64, and then you subtract 8, which are the same. In other words, first choice, first scoop, you have 8 flavors to choose from. Second scoop on your dish, you have 7 to choose from. 1 less. So it's 56. So her answer is actually correct, even though she did a slightly different way. And she said excluding these, basically that's correct. Because once that's chosen, once the first scoop is chosen, you don't choose it again. So if this is correct, then her answer is also correct. So if she had explained that she assumed the order matters because the right side and left side, say, matters according to her interpretation, then it's correct. So should I give her a bonus mark? Anybody object if I give her a bonus mark? Okay, let's give her a bonus mark. Like I said, you better explain why order matters in your case. Even though it's not, to me, it doesn't matter, but it's subject to interpretation. So make your assumptions. And if you answer correctly according to your assumptions, then you'll get at least most of the marks. And do you know who she is? What's her name? Do you know her name? What's your name? Shema. Okay, correct. Good. You don't get a bonus mark for that, but you're correct. Okay, we answered the other way. If we say order does not matter, then what? Okay, you think about it, you can answer it. Let me go to the last one. Ice cream shop again offered different flavor ice cream. How many different 2-scoop desserts are possible if the 2 scoops are placed one on top of the other? So now, instead of a bowl, Vincent, you ask for a cone. And you stack them. Lime, chocolate. So order matters. So the answer is this. And it's permutation. So looks like, sorry, it's not correct. So he answered order list, which is this. Repetition is allowed, but actually repetition is not allowed. Because 2 different ice cream scoops. And also, order matters. So it's actually permutation. The answer for the last part is supposed to be this. So in other words, this is incorrect. That should be permutation. And that should be 8 times 7, 56. Switch. No, he put down order list, repetitions allowed, which is not correct. So this is also not correct. Even for you, repetition is not allowed. Different, same thing, different 2 scoop, different 2 scoop. So we have 1 bonus mark today. Well, so far. Okay, let's move on. Actually, I'll just leave you for those. You can do it yourself. Okay. So let's try to look at counting. Are you good at counting things? How many scoops you have? You're very good, right? I ordered 2 scoops. You better give me 2 big scoops. Well, we can use a table or a tree structure to organize these lists, things you're trying to count. So how many different permutations are there for 3 letters, S, E, and T? So if it's SIT, then it's a school here. SET could stand for Stock Exchange of Thailand, for example, or just SET. But the 3 letters, S, E, and T. So how many different permutations? We call it permutations because ordered matters. And repetition in this case, repetition is not allowed. Repetition not allowed, order matters, we call it permutation. So SET, in this case, we meant a permutation because I asked you permutations. So this is very simple. First one can be 1 of 3, second one of 2. 3 times 2, so 6. Next, same thing, order sandwich drink, there are 6. So basically, very similar problems. You can actually go through them yourself. And then how many subsets are there? So in other words, the power set. What are the elements in the power set? So how would you represent it in a tree structure? It's not mentioned here. So when we do a tree, for example, let's look at this. So we can start off with S, and then remaining. So basically, this is the root beginning. We can have S, E, or T. And then after you choose S, you can have E or T. And then afterwards, this is T, and this is E. And so on. So it turns out in this case, no, that's all. 1, 2, 3. Is that right? Yeah. Sorry. And then one more at the end. So we have 1, 2, 3, 4, 5, 6 cases. So that's a tree structure representation. Right? So you have seen this before, I'm sure, somewhere. What about table? How do you represent it in a table? So table form, that means just list it, right? So you can put it in a table. Different ways. If you want, you can put, it shouldn't be too close to the microphone. But you can put things like S, E, T. You can put first, second position, third position, if you want. So you can put down, I mean, any of these are possible, right? Is it? Well, actually, you should be. If first is S, then second can be E or T. So it's not quite the same, but you have to list them. Actually, I should put it a different way. There are different ways to put it. You can put, just listen in order, S-E-T, S-T-E, and then E-T-S. E-S-T, T-E-S, T-S-E. Or something similar. I'm basically listed out in a table form. Okay. So what we can do is you want to look for if it's a combinatorial equivalence. That means if any of these two or more combinations are the same or not. So if you have two lists, you want to see if the length is the same. If the two are the same, that means possibly it's the same list or same combination. What we want to do is to find a one-to-one correspondence between the two lists, say given two lists. In other words, what we just talked about in your quiz, try to find a one-to-one correspondence and then we're looking for an invertible function. Okay. All right. We'll look at the example when you come back from a break. So we'll continue again after the break. Let's just take 10 minutes break. At least I'll start again after 10 minutes. And those of you who were late coming in and missed the attendance checking, you can come up and write your name. Okay, I'll start lecturing again. So let's hope the other people will come in again. Okay. So we're talking about combinatorial equivalence. That means it's the same. How do we know if two lists are essentially the same or counting the same thing? So if two different lists have the same length, for example, so it doesn't matter how long each list is. We don't need to know how long it is. But if we know there's something in common between these two lists, we can say, combinatorial speaking, they're equivalent in terms of the length. So that would allow us to find basically a one-to-one correspondence between the two lists. If there's a one-to-one correspondence, one element from one list goes to one element in another list, one-to-one only. In that case, that means the two lists will be the same size. Because one from one goes to one to the other. So exactly one-to-one, that means they have the same size in terms of length. So this is what we need to identify invertible functions. So let's look at an example. So these two statements, or these two questions we ask, actually have the same answer in terms of how many. So first, okay, let's look at the easy one first. How many numbers are in the set basically from 0 to 999? Okay, that is straightforward to imagine. You have 1,000 integers from 0 to 999. So how many numbers are there? Well, you can calculate, it doesn't matter, but you don't need to. Now imagine we ask the question a different way. How many ways are there to distribute 3 coins with a penny, a nickel, and a dime? Penny is one baht, nickel is 5 baht, and dime is 10 baht. And we want to give the 3 coins to 3 children and each person, or to 10 people. And each person may receive more than 1 coin. So we have to put that in there. So to map the correspondence, you can say, well, if you look at this set of numbers, what we have are 3-digit numbers. In other words, we can write 0 as being 000, and then 001, 002, all the way to 998, 999. So this set of integers from 0 to 999, we can imagine it to be 3-digit integers. Because we can put a 0 in front of, and say dot dot dot, then 011, 012, dot dot dot. Put a leading 0 in front of these single and double digits. In effect, we have 3 digits. And the 3 digits can correspond to 3 different coins. So this could be the first coin, second coin, third coin. Okay, so now we have 10 children. The 10 children corresponds to the 10 digits. So as you can see, if we put it that way, we actually have the same, it's a very similar question. and the answer would be the same. So this is an example of combinatorial equivalence. Is that clear? So we just illustrated that these two questions lead to the same answer. In other words, they have the same length. And we're mapping 1 to 1. So in the first case, we give all the coins to the first child. Second case, give the coins 2 to the first child, 1 to the second child, and so on. In the last case, you give all the coins to the 10th child. So it's equivalent mapping between these two questions. Okay, so the second one is actually related to the assignment you just submitted recently, which we talked about before. We talked about the power sets. So the number of subsets of this is a power set of this, and we said it's 2 to the power n. So basically, number of binary sequences of length 10 is 2 to the power n. So we can also map 1-to-1 correspondence to this example. Okay, so now I'm giving you another practice scenario, and I'm telling you 1 and 2 here in Roman letters they should have the same answer. We want to see if you can give a 1-to-1 correspondence between this and this. So the first one, it says how many distinguishable arrangements of the letters A, B, A, B, A, B, A, B, A are there? So distinguishable means you can tell the difference. So what you see here is that you have what? 2 letters, A and B. Right? So this is this one possibility. You can also have A, B, B. So 3 A's and 2 B's. How many ways can you arrange it that's different? So the order matters. In the second case, you ask how many 5-digit binary sequences. So binary sequence means it's 0 or 1. A sequence with 5 members, each one is either 0 or 1. A binary sequence, 5 digits. But then, more specifically, it says, how many of these sequences are there that there are exactly 3 ones? So you can see the equivalence here. 3 A's and these 3 ones. So you can map the equivalence. Each case is binary. 0 and 1 here, and here is A or B. So both of these cases are binary. And both of these cases consist of 3 of one of the elements. So in that case, we can map 1-to-1. It's a 1-to-1 correspondence. So these two should give you the same answer. So if you want to write the same form as that, we can write the binary digits as being 1, 0, 1, 0, 1. This is the equivalent to A, B, A, B, A. Okay, so I didn't ask you, the question does not ask, actually it does ask you how many, this and this, 8, 1 and 2. But the practice is to explain why 1 and 2 should give you the same answer. So in other words, I want you to show the one-to-one correspondence rather than answering each of these questions. You can answer it, but this only requires you to show that there's a one-to-one correspondence. So first, we show that both are binary. So we have either 0, 1 versus A, B. Then in this, the other one corresponds as 3, I guess, members, elements. This is called 3 members, isn't it? One of the well, depends how you write it, and 2 for the other. You can write whatever form you want, but basically showing that it has the same structure. So there's a one-to-one correspondence in answering how many. Okay, you can write your own words describing it, and then that will be fine. Okay, another one. It looks different, maybe, but we also try to use one-to-one correspondence to explain why below should have the same answer. So the sets have 5 elements. We want to compare how many 2-element subsets versus how many 3-element subsets. So why are these 2 equivalent? In words, it sounds different. One is a 2-element subset, and the other one is a 3-element subset. So why would these 2 be equivalent? Well, the key here is to recognize that total there are 5 elements. So if there's a 2-element subset, that means the complement is a 3-element subset. So we're looking at complements. Because there are 5 in total. If you choose 3 as being subset S, then S prime is, this one has is a 2-element subset. So in that way, there's a one-to-one correspondence. So we have 1, 2, 3, 4, 5. So if you say a subset is 1, 2, 3, then the complement of that is 4, 5. This is 3 elements, and this is 2 elements. So there's a one-to-one correspondence. So basically, you're mapping, say there are 20 3-element subsets. That means there are 20 complements of these 3-element subsets, which happens to be 2 elements each. So that's why we count the same thing. See some confusing faces? You can say the whole set consists of 5 elements. 1, 2, 3, 4, 5. If you choose a 3-element subset, remember we're asking how many 3-element subsets. So we have to choose 3 of them. Say 1, 2, 3, or 2, 5, 4. We choose 3 of them out of this 5-element set. So if we choose one of these as 3 elements, then we know, because total there are 5, the complement of this consists of 2 elements. So for each 3-element subset, there's a corresponding 2-element complementary subset. So it's a one-to-one correspondence. So it doesn't matter what the answer is, the answer will be the same for questions 1 and 2. Okay? So this is something that you should try to look at it more carefully afterwards. Talk to your friends if necessary, or come talk to me if it will help you. To help you to understand this concept of one-to-one. Okay, so we move on. I wanted to finish that actually before the break, but that's fine. Now we're going to basic rules for counting. Very simple. First rule is the rule of products. Okay, so let's say we can create a list, and then first member of the list we can choose from X objects, and then one from the Y objects the second one. So for example, it could be one of 10 digits. It's a two-digit number. One is the first digit is either from 0 to 9, second is from 0 to 9. So we can talk about total, that means there are 10 times 10 possible entries, or 100 numbers between 0 and 90, from 0 to 99. So that would be 10 times 10. So we call that rule of products. We look at the possibility of selecting the first object, and then possibly selecting the second object, and the total number of objects simply the product of the two. So we call it the rule of products. So the number of elements in sets A cross B is equals to number of elements in A multiplied by number of elements in B. So this is something that we've been using all along, but we're now giving it a formal definition term called rule of products. Products means it's a multiplication of two numbers. So it's just a definition, you can say. So a similar example to what I just gave is this. How many numbers between 100 and 1,000 have three distinct odd digits? So let's try to walk through this and get an answer. Okay, so between 100 and 1,000, we have 101, 102, 103, and so on, all the way up to 999. Okay, so three-digit numbers. These are three-digit numbers. Have three distinct odd digits. So the three digits are odd and they're all different. So for example, 133 doesn't count because 3 and 3 are the same. These are all odd, but 3 and 3 is the same, doesn't count. 1, 2, 3 doesn't count because 2 is even. But 153 is one of the entries, one of the numbers, because 1 is odd, 5 is odd, 3 is odd. And they're all different. So distinct. So how is this related to what you're going to do later? Because when you're given, you can think about when you have to do a program, you have to understand the requirements. And you have to interpret it correctly. So in a way, you have to make sure you can read things, understand everything clearly, and you can look at equivalence. So when you're doing coding, maybe you already coded for number 1, but you ask question for number 2. But you show us a one-to-one correspondence, that means I can use the same module that I already coded for 1. I don't have to code it again. This is reusing. It's making it more efficient. Okay. So, but like I said, you have to understand the requirements. In other words, you have to read this carefully and understand the statement. Because when you're coding quite often, when you talk to a client and they give you requirements, you think this is what's correct. You go and code. But you need to communicate again with your client clearly to say, okay, these are the requirements, steps 1, 2, 3, 4. Output would be in this form. And you have to make sure that they approve and say, okay, this is correct. So in other words, same thing in the sense that you have to read these things carefully and understand it. And if you don't understand it properly, write down your assumptions, if you have any. Because it's what you will show your client. Say, okay, I'm doing this according to this, and this. Is this what you want? And then if they say no, okay, then you try to modify it. And before you actually do the start, so the requirements, you need to make sure you satisfy them. So in your case, you need to make sure you understand the question that's asked in this course. If you don't understand that, then you have to make assumptions if necessary to show that, well, if this is my understanding of this is correct, then this is how I do it. Or you can ask a question in the exam if necessary and say, this is my understanding, is this correct? Then at least I can tell you your understanding is correct or not. Okay, so to answer this question, how many numbers between this and this have three distinct integers or digits? So basically odd digits are 1, 3, 5, 7, 9, right? 5, one of 5 possibilities. And they have to be distinct. So the order matters, right? So 153 is not the same as 513, and not the same as 315, and so on. So the order matters, and they have to be distinct. And we have choose from 5 digits, 1, 3, 5, 7, 9. So imagine you have to choose 3 blanks. Basically, we have 3 digits. From 101 to 999, there are 3 digits. And you fill up with one of these choices, 1, 3, 5, 7, 9, because it has to be odd. So the first blank, you choose 1, 3, 5, 7, 9. Second one, you choose from, so this is a list of 5. When you take one of them, second one cannot be the same. If you choose 7 here, then 7 is gone. You only have 1, 3, 5, 9 left. So this is 5, this is 4, and 3 remaining. So 5 times 4 times 3. Right? That's how you answer this question. Okay, choose one of 5 and then choose a different one of this. That means only 4 remaining. Choose another different one. That means only 3 remaining. So it's 5 times 4 times 3. Use the product rule, which we talked about before, but I just defined for you. It's called a product rule. Okay? So 5 times 4 times 3 is 60. So 1, 2, 3, 4. Well, there are 60 of them here. You can count if you want. 5 times 12. Okay, so this is the answer. So a question you may encounter in your assignment, quiz, exam, something like this. An organization has 10 male and 7 female members. In how many ways can the organization select a president, vice president, and secretary if the president must be female? So we give a constraint first. So we have 3 positions. The first position is president. But the president has to be a female. You choose from one of 7. And then the second one, you have vice president, you have secretary. So how would you answer this question? And by reading this, you also assume that the president, vice president, and secretary are 3 different people. It's possible one person assumed the same role, but normally that's not done. So the assumption you would make is that 3 different people would be elected somehow to be the president, vice president, and secretary. So first, pick the easy one, the constraint. The president must be female. 7 ways. 1 of 7. If it's a random, we're assuming it's the equal chance. But let's not go into probabilities for now. So we want to pick the 3 positions: president, vice president, secretary. So president, 1 of 7 possibilities, right? Because it has to be a female. So what about vice president? He has 16 left. So we have 17 minus 1. And then the last one, well, 17 minus 2. If it's totally random, right? You just said how many ways, that means the possible combinations. So it is 7 because you have to choose from female. This is 17 because it's female plus male, means all of them. But one is already chosen, cannot be. So we're saying there's no repetition, because once someone's elected president, they cannot be a vice president or a secretary. That's the assumption we can put in here. It's not specified. If you want to assume it's possible, then you write it down, because it's really an assumption in your case. What about the second one? What have we changed the constraints? So we changed the constraints and said this president can be male or female. Vice president must be female. And secretary must be male. So the case is actually quite simple because it doesn't overlap. So it has to be a female. So this is 7. It has to be a male. These two don't overlap. And then this is 17. We already chose 2. Would that work? Any questions? Okay. Next question. How many binary strings of length 5 are there? So you interpret it. Binary, again, it could mean 0, 1. String of length 5. So 5 digits or 5. So you have to make sure you interpret it properly. If you have a different interpretation, then state it and answer the question. So in this case, we have 2 different elements, 0 or 1. 5, is repetition allowed? Is the order matter? Being a string, order matters. And repetition, it's allowed, right? I mean, you can choose 0, 0, 0, 0, 0. That's one of the strings. Actually, it has to be allowed because there are 5 length of 5. Only two possibilities. At least one of them has to appear more than once. Okay, so you can answer these. Another one, maybe you imagine a dice. So in this case, like in your stats class, maybe introduced to the concept of experiment. So in this kind, the experiment is to rolling a dice 5 consecutive times. So the outcome of each dice roll is 1 of 6. So you get a face value of 1, 2, 3, 4, 5, 6 for a standard dice. And you roll this 5 times. So it could be 6, 1, 2, 3, 3, for example. So you roll it 5 times. What are the elements? So when you ask this question, how many different results are possible when a 6-sided die is rolled 5 times? You have to interpret what it's asking. Is it asking what are the different outcomes and the order matters? Or it doesn't matter, but you just say how many 1s, how many 2s, how many 3s? Or are you asking the sum of the 5 dice? It's not clear here. It just says how many different results are possible when this is rolled 5 consecutive times. So if it's not clear, then you state it, whatever assumption you make, this is what your understanding is, and you answer how many according to your assumption. And that's why it's important if someone asks you to code, for example, you have to understand the requirements. Because statements like this can mean different things. When you talk to someone, your interpretation may not be what they meant. So it has to be very clearly communicated. And you have to go back and forth maybe more than once. Okay, so you can try these questions as practice. Okay, so similar to what we have looked at for power sets, we're saying the number of order list of length k with entries taken from this is n to the k. So what is an order list? If you remember way back at the beginning, order list means order matter and repetition is allowed. When repetition is not allowed, then it's called permutation. So we're talking about order matters, either an order list or permutation. Okay, for order list, the number is n to the power k. For permutation is, in this notation, p for permutation, p permutate n, and you choose k. So what's the short form for this? It's just n factorial divided by How do you express this? It's not n factorial because only first k terms. So you have to remove n minus k factorial, right? Okay, so I'll do it right after. I guess it's too simple to show somewhere. So you can write it this way if you want. N minus 1, n minus 2, and so on, multiplied by n minus k minus 1. And then n minus k plus 1. N minus k plus 1. And then n minus k minus 1, n minus k minus 2, and so on. That means n minus k factorial is divided from n factorial. This is the notation. I think you've seen this before. And this is same as n because n minus n is 0. So this n factorial divided by 0 factorial, which is 1. So it's n factorial. Okay, I guess I can write it for you. It's pretty obvious. I think you've seen it before. Okay, look at an example. So similar to before, we have 10 male, 7 female. How many ways can we select a president and vice president? If the officers must be of the same sex. Another constraint. So first, it's either male or female. Once it's chosen, then all the officers, president, vice president, and secretary are from the same sex or same gender. So we're going to look at two scenarios, if you like. Basically, it can be one of two genders, male or female. So let's look at the case of male. Male, the 10 is 10 times 7 times 10 times 9 times 8, right? So we use this permutation of 10, and we need 3 of them. Permutate 10 and 3. Then we get 10 factorial times, 10 times 9 times 8. And if it's female, then it is 7 times 6 times 5. Or 7 factorial divided by 7 minus 3 factorial, which is 7 times 6 times 5. So how do we answer this question? Are the two events Do they overlap or are they independent? So two scenarios. One is male executive team, and the other one is female executive team. So they're both possibilities, right? How many ways can one select a president? So either male or female. So we get the answers for this and this. And the answer to this is this plus this for total number of possibilities. So we add the results for this, for male, to the results for female. So we have 10 times 9 times 8 plus 7 times 6 times 5. So 720 plus 765 is what? 210. $720 plus 310 is 930. Is that correct? Okay, so easier to break it down into two, and then we just add the results because they're two independent cases. One is if it's a male executive team, the other one's a female executive team. That leads us to rule of sums. That's why we add them. If A and B are disjoint, like in our case, male and female executive teams are different. If you're male, you're not female, and vice versa. So they're disjoint. So when we're looking at the union of these two, it's simply adding up the number of, in each case. So number in male, number in female, give you the total. So this is the rule of sums. We talk about rule of product, and we use that to calculate for each of these. But now, next we use a rule of sums because these are two disjoint, independent scenarios. So we can add the probabilities when they're independent. No, sorry, not probability, the number, the count. Talking about counting. The probabilities we need to divide by total number of cases. We haven't talked about that yet. Just counting. This is count. How many ways? So how many? Just counting how many. So this is rule of sums. So in the case of the example, we can split into two disjoint pieces of, so male and female. And total number of 17 employees. Okay? Okay, a practice question, another one. Again, we have a 6-sided standard dice, 1 to 6. We roll 3 times. And we record the results ordered. So this is very specific now. Order matters. So let's say we get 3, 1, 5. So that's different from 1, 3, 5. How many of the possible outcomes contain exactly 1, 1? So first, you have to answer how many possible outcomes are there? And then find out how many of them contains exactly just 1, 1. Like 5, 1, or 3, 1, 5 contains 1, 1. 1, 3, 5 also contains 1, 1. Because order matters. So to answer this, one way is to divide the list into 3 disjoint sets. So imagine you roll it three times. So the first time, it may contain a 1. Second time you roll, it may contain a 1. Third time you roll, it may contain a 1. So they actually divided into 3 disjoint sets. First disjoint set is your first row. Second disjoint set, second row. Third is the third row. So basically when you roll this, suppose if the outcome is random, there are 3 independent events, disjoint. The outcome from the first row does not influence the second one, does not influence the third one. So the disjoint independent events. So we can imagine it that way because we rolled the dice 3 times. So the 3 rows. So now if you divide into 3 disjoint sets, then we can calculate for 1, for 2, for 3, and we add it up. So the answer is simple, right? The first row is 1 of 6. Second row, 1 of 6. Third row, 1 of 6. So the total number of possible outcomes is 6 plus 6 plus 6. Is that correct? Or not? No, it's not correct. Total possible outcomes is 6 times 6 times 6, product rule. But we're talking about containing exactly 1, 1. So what do we do? P11. What about P61? What about P61? So you don't use rule of sum, you use rule of products only. Well, the hint here is I divide into 3 disjoint sets. First, those where the number 1 dice is the first row. So when it's the first row, then didn't quite finish, but so 3 disjoint sets. First, row is 1. So first throw is 1, that means, well, he said P11 because only 1. That means it's actually 1. Yeah, it's only a 1. And then he's saying the remaining is P61. Does that make sense? It cannot be 6 anymore. There are only 5 digits left. there are 5 digits left. Because 1 is chosen, this cannot be 1. It's either 2, 3, 4, 5, or 6. 2, 3, 4, 5, or 6. So actually we're looking at 1 times 5 times 5, 25. Is that right? Second scenario, second throw is 1. So that means the second one is this. First one is not a 1. Third one is not a 1. So it's 5 times 1 times 5 goes to 25. You do the last one. Third one, you get 155, 515. Last one is 5 times 5 times 1, 25. You got 25 plus 25 plus 25. So product rule to calculate each disjoint set, sum rule to add them up for the 3 disjoint sets. For each disjoint set, there are 25 possible combinations. And since they're distinct, this count is different from this count, different from the last count. Does that make sense? Any questions? Again, it's most important to understand this question. And if necessary, write down assumptions. Okay. So in a similar problem, how many 3-letter sequences of the Greek letters? Alpha, beta, kappa, epsilon, whatever. And there are 24 letters of the Greek alphabet. So how many 3-letter sequences of the Greek letters do not consist of 3 of the same letters? That means it cannot be alpha, alpha, alpha. But it can be alpha, alpha, beta. Alpha, alpha, beta is 3 of the same letters. Now, how do you interpret it? Meaning alpha, alpha, beta is permissible, or has to be alpha, beta, kappa, all 3 different? Sorry? Think about it more carefully. Again, we have to divide this into disjoint sets. Because you have 3 cases. Similar to this, isn't it? Okay, so think about it. We don't have to finish this in class, but you should be thinking about it after class. You have to do some self-study. Okay? So next section is on combinations and the binomial theorem. You heard of binomial theorem before? I think you have, or most of you have. So we talked about combinatorial equivalence. That's when we can find one-to-one correspondence between two different scenarios. So we can say the number of elements will be the same in those cases. So the length is the same. For equivalence relationship, it's a relation on a set between a set and the partition. So we have a set, for example, before I said 1, 2, 3, 4, 5, we can have partition 3 elements and 2 element partitions, because 3 and 2 give you 5. So we divide into one 3 element partition, another 2 element partition, for example. Here. So let's say a set 1, 2, 3, 4, 5. In this case, we have a partition, 3 different partitions, 1, 4, 2, 5, and 3. So we have a 2 elements, and a single element partition. So what is the rule here? We want to, given a relation, it's given by this rule, the set is 1, 2, 3, 4, 5. The relation is that we have an ordered pair xy. So if x minus y is divisible by 3. So the order matters, but in this case the answer is the same if it's yx or xy, because it's negative 3 and 3 are both divisible by 3, for example. But of course, if it's a partition, 1, 4 and 4, 1 is the same partition, right? Okay, so basically we say x, y, x belongs to this set R, y belongs to this set R. So what it means is x and y can be the same, right? That's why I say, so x, y is 3 and 3. But the partition is just 3. So the order pair is 3, 3. But it only consists of one element, 3. Okay, so you can see in this case, these 3 partitions, 1, 4, 2, 5, and 3, satisfy this relation, that x minus y is divisible by 3. Okay. Let me just go back. Any questions? Okay, so again, the definition, we're trying to say equivalence relations. We define that as a relation, in this case R, satisfied by this rule, on a set, in this case set 1, 2, 3, 4, 5, that would give the outcome that is a partition of A. So the outcome in this case is the sets 1, 4, 2, 5, and 3. And this 3 sets happens to be partition of this. So if that's the case, that means there's equivalence relations. This is an equivalence relation, R. So the equivalent relations is a relation that's defined such that when it operates on a set A, it produces a partition of A, like in this example. Okay, so if this is true, then this relation R is an equivalence relation. Okay, it's just a definition. Okay, so look at another word problem. Because there tend to be more and more word problems. How many 3-element subsets of 1, 3, 5, 7, 9 are there? So 1, 3, 5, 7, 9 has 5 elements. You want to take subsets of 3 elements. So basically, we have 5, and we're trying to have 3 of them, right? So permutation of 5 and then length 3. Because 135 is same as 315, same as 531. It's the same, it's a set, it's the equivalent set. So repetition is not allowed because in a set, the elements have to be distinct. You cannot have 1, 1, 3 as a set, because the set is actually 1, 3. And the order doesn't matter. 1, 3, and 3, 1 is the same set. Okay, so basically the same way we have counted actually previously. So if you count as a permutation, that means the order matters, then we get this. But if you say the order does not matter, then we actually divide it by that means these are the same, right? And these are the same. So related to this, after we have done the permutation with the order as being important, let's look at the equivalence relation. So the equivalent relations is x, y, the order pair, in this R. If permutations x and y use the same 3 letters. So for example, 137, 371, they're the same 3 digits. So if you look at it visually, then it's pretty straightforward. So the one in here, 913, 139, 319, 931, 193, 391, 1, 2, 3, 4, 5, 6 of them. We consist of one partition, or one subset. Another one could be this brown one, and the other one's the purple one, and so on. So what you see here visually is that these partitions are disjoint. So if 139 belongs to this partition, it does not belong to any other partition, any other subsets. Or the relations, so if this is a relation, to satisfy this relation, we can have different subsets. And these subsets are disjoint. So since it's disjoint, and it consists of the entire domain, then this is actually an equivalence relation. Because this relation will partition it into different subsets. And as you can see in this case, each subset has 6 elements. And if we say the order does not matter, like I said, then basically we take something like this and we'll divide it by, so this is leading to the concept of choose, right? So 3 factorial is 6. If the order doesn't matter, then you say choose. Or combinations. So permutations, P, C, combinations. So you can answer this question, how many different colors are used? That means each color has 6 elements, but how many different colors would that be? So you should be able to answer that quite easily. Okay, so that would be a question, a question that we could ask very simply. So multiple parts. Usually a question consists of multiple parts. You answer some of these, and one of the parts could be how many different colors are used, for example. Okay? So basically it's asking you when it's partitioned, how many partitions are there? So in this case it's very simple. The answer is 10. There will be 10 different colors. Well, you'll figure that out. Okay, right here. Total permutation of length 3 from this divided by 3 factorial is this divided by 3 factorial equals to 10. That's the number of partitions. And these are the 10 possible combinations. Similarly, we can actually generalize this to, say, n elements, and we choose a k element subset. So here we have 1, 2, 3, 4, 1, 3, 5, 7, 9. But here we can generalize it to an n element set, and we want to have k element subsets. So generalize it. So what we have is basically the formula I just gave you here, combination. Combination of n, choose 3, choose k, is basically this formula, which is this formula divided by k factorial, which is this formula. So this is something that you have seen before as well, but just I'm showing it to you again here. So you can practice these permutation, combinations, calculate these very easy. That would be very easy marks if you have to do this. Just have to be careful. So as an example, you can go through this. It's, again, understanding the question and interpreting it properly, correctly, is the most important thing. Okay, so you can go through that. Another example. I'll just stop here. Before, we won't go into the Pascal triangle or the binomial. We'll cover that next time, plus something else. Okay. There's one thing I need to inform you. Actually, maybe I'll give you a choice. Next week, I'm not here. Physically not here. So your choice is, I can give the lecture electronically, I'll be somewhere else, and you'll be listening to me, and I can give you a lecture, or we will schedule it for another time. Do you want to keep the same time by maybe I'll ask Ajahn Pontai to come in, but I'll give the lecture, but I won't be physically here. But I will be doing it on the screen for you. And I'll go through the material. Or we can schedule it another time. Actually, a third choice is simply to ask Ajahn Pontai to teach the class, I guess. It will be after the break, yes, because I will be away the whole week next week. Well, actually, I come back on the 10th. When is the break? 7th of April? Okay, then. Yeah, I won't be here. I mean, it will be after a break for sure. Because the class on the 5th, right? Next Wednesday is the 5th. You don't have anything? You out? Okay. So maybe you want to reschedule it then, because, it's up to you. You can come here next Wednesday, same time, and I'll arrange for e-lecture